Welcome everyone. My name is Greg Risteman from Olympus NDT, and I'd like to welcome everyone today to this installment of our webinar series entitled Introduction to Phased Array Inspection Using the OmniScan MX2. Today's webinar is part 3 of the series and will cover gate and C-scan configurations for weld inspection, calibration options and limitations, and include explanation and demonstration of the OmniScan MX2 calibration wizards for manual inspection. Our presenter today is Chris Magruder. Chris is the Phased Array AUT Manager for Olympus and has been developing and delivering phased array systems for over 12 years. This webinar will last approximately 60 minutes. If you have questions, please type them into the Q&A panel in the lower right portion of your screen during the course of this presentation. Do not type your questions into the chat panel as we do not monitor chat for Q&A. If we don't get to your questions during the live webinar, they will be addressed personally either by email or by phone after the event is over. Now, without further ado, I'd like to turn the presentation over to Chris Magruder. Chris, it's all yours.
Good morning and good afternoon, everybody. Thanks for attending. This is one of our biggest turnouts in this series of webinars. We see representatives from almost all of the continents joining us today. Again, I'm Chris Magruder, the AUT Manager for Olympus, and this is part 3 of our Introduction to Phased Array using the OmniScan MX2. So before we get into today's topic, we're going to briefly review what we have done up to this part. In our first couple series, our first 2 series on the MX2, we started with the wizard, which is where we create all of our groups and perform various common functions. We populated the part, which is basically telling the velocity. We went through the setup and the focal laws, and today we'll be going through the calibrations and talking about a little bit more in-depth use of the instrument. So to review what we've been working on, and all of these come from the wizard parameters, we have a 5L64 probe with a basic shear wave wedge installed. These were all completed during the wizard. In our focal law, we programmed a sector scan on pulsar 1 of the instrument. We're using a 20 element aperture. So in this case, we're simulating a ½ inch probe. 0.6 millimeters times 20 equals 12 millimeters. So we've designed about a ½ inch probe and a standard 45 to 70 degree sector scan at a 1 degree resolution. So when we look at the S-scan, as I move it back and forth, we notice it is flat, the shape is normal, it looks good, it's at the correct depth. There hasn't been any calibrations performed yet, just a basic overview of the UT settings for the range and the filters. So we've set up the basic group, and from our wizards, we're going to talk today about the various functionality for sensitivity, velocity, and wedge delay, and what those mean and how we use them in the instrument for our inspection. The first part of this is the velocity we're going to talk about. The velocities of the wedge and component material are 2 of our primary ingredients. We must know them to be able to form the group. No velocity correction can be made without recreating the focal laws. So although the velocity wizard appears in the calibration, what you're really doing is breaking all the focal laws and rebuilding when anything is made. The velocity is directly related to beam angle, like Snell's law. A material velocity error of no more than 20 millimeters or meters per second must be entered into the calculator if we expect a 1 degree angle accuracy tolerance. In other words, velocity is related to angle. If either the velocity of this wedge or the velocity of the material you're inspecting is other than what the software thinks it is, the result is angle error. Excuse me. Sorry about that, folks. I laid my mouse down. In the wizard, the velocity parameter can be set and calibrated. It appears in two places: in the part weld wizard setup, in the part weld setup, and in the UT parameters. The velocity can be either calibrated or entered in directly if it's known. And again, modifying the velocity will remove any calibration that was previously done for sensitivity or wedge delay. The preferred method of obtaining the velocity in a group setup wizard is to select the material from a fixed database using the default value. In other words, the preferred method, the overall most accurate way of obtaining your angle is normally achieved by selecting the velocity directly from the database. In the pipeline inspections and in applications where it's extremely critical, we know the precise velocity of the material, we build a block like this. It's a standard from an API pipeline inspection. This allows us to measure the velocity at 0, 45, 60, and 90 degrees in each axis of the component. Without that block, measuring the velocity on the IIW block verifies the instrument's capability of measuring velocity, but it doesn't tell you anything about the real velocity in the component. In other words, a slight difference in the velocity between a standard calibration block like you see here for shear wave angle beam and 0 degree L wave would result in a slight angle error on the material if it were not made from the exact calibration block. Additionally, measurements made so that the velocity can be more accurately entered than the database requires about a 20 meter per second accurate reading. That equates to about a 0.1 millimeter in the sound path. So to beat the database velocity, you must be very, very precise. Only precision measurements to this tolerance can be made on a block of the exact same material. The MX2 velocity calibration wizard has three options for velocity: a radius, a depth, or a thickness. Depth and thickness essentially work similarly in that they're designed for a side drilled hole at 0 degrees, whereas the radius is possible in a shear wave angle beam inspection, and that's what we would normally use. In the wizard itself, we select the velocity of the mode and select start. Prior to doing the velocity, I inserted this slide to mention that it's very important that you know what gate measurement mode that you are in. Normally, we're going to use for weld inspection peak amplitude, which is denoted here by E. When we calibrate or when we measure anything, the reading we receive is directly related to the gate mode that we're in. And it could be leading edges, first peak, or max peak. And again, max peak is typically associated with weld inspection. D and E would be amplitude-based applications, whereas A, B, and C would typically be corrosion, time of flight, or composite inspections. The readings are also directly related to this, and we use the readings throughout the calibration process and throughout our inspections and analysis. So be aware of what reading that you're in and how it affects the application. So back to the velocity wizard. Just like any conventional digital instrument or any other phased array instrument, to calibrate a velocity or to measure a velocity, we're basically going to take two known positions in either sound path or depth, and the software will calculate the time of flight between them and arrive at the velocity. When we're calibrating velocity, it's only relative to one A-scan. In other words, we're going to select one A-scan at one angle and do all of our measurements based on that. Although there's a slight velocity difference for different angles, the instruments, modern conventional digital instruments for UT or phased array, typically only allow one velocity for the group. And in this case, we'll have selected this blue line for the A-scan and identified back wall 1 and back wall 2 at 25 and 50 millimeters. The software is going to ask us to set the gate over position 1. So we move it appropriately into this, select get position, and the software will record the peak value in time of flight. And then we repeat the process for the second position. Any two known positions, whether that's a radius at an angle beam or a back wall at 0 degrees, with two known positions, the software can calculate the velocity. So prior to accepting it, the velocity is visible here. That was calculated. Upon accepting it, the velocity is automatically placed in the UT parameter, and a green V will appear in the OmniScan user interface. This green V is not an indication that something was calibrated or not calibrated. It was simply an indication that the velocity was measured using the MX2 wizard. More than likely, in most of our customer experience, they're measuring the velocity of the cow block and not actually measuring the velocity of the component they're working on, which amounts to the exact same thing as selecting from the database. Again, a very minor deviation in your ability to measure it would make the database accurate, more accurate than a typical group of 5 people taking 5 readings. So a question, if the material velocity for the component is unknown, what is the benefit of performing the OmniScan MX2 velocity wizard calibration on an IIW block? And in reality, there is no benefit other than verifying the instrument's ability to measure velocity. Only in a block made from the exact same material will a true velocity giving us the true angle in the material be possible. But as conventional tradition for UT, it's often verified on this block with a 50 or 100 millimeter radius. And again, we would recommend selecting it from the database in the instrument if this block is not available. What is the effect on focal law creation using wrong or inaccurate material velocity in the wizards? Answer is angle, focus, wedge delay, calculation, error. Of all of those, only the wedge delay can be corrected in the calibration wizards. Often, they make a correction to this wedge delay to fix an angle error, but as the hole or calibration target above or below it is visualized, you'll see the inaccuracy. Moving on to wedge delay, I'm going to go back to the instrument for a moment. And transition back to our setup on the instrument. Here we see our basic setup, and as I move the probe over a side drilled hole, and we can see I'm looking at the side drilled hole here of an IW block at 15 millimeters. The group hasn't been calibrated or nothing's been done. We've exited the group wizard and adjusted the UT settings. But prior to calibration, I want to move the probe over the calibration block, and I can see that the depth is correct at 15 millimeters. If I go to different angles, I can see that it's consistent, straight, and flat at the correct depth. What that tells us is that the software under Beam has calculated from the wizard our wedge delay correctly. I can perform the wedge delay function, maybe tweak it a little bit, but in accordance with the codes, in accordance with a conventional UT, my ability to verify this position prior to calibration verifies both the velocity of the wedge and the wedge delay that was calculated by the calculator. So we want to be careful not to downgrade our calibration with a large side drilled hole or by trying to fix an angle error or velocity error that's not really our problem. So going back to the PowerPoint presentation, the wedge delay the wedge delay can use a side drilled hole or a radius. If the side drilled hole depth changes across the different focal laws, it's normally an indication that a parameter from the calibration, or excuse me, a parameter from the calculator is incorrect. If the side drill hole is at a consistent position and straight and flat, it's an indication that our initial setup was very, very close. What wedge delay does from our A-scan, it calculates the time of flight through the wedge in microseconds for every beam, exactly like conventional UT. The velocity is known, the position's known, so the software can make that. This is no different than conventional UT, except that we're doing it over many different angles. So like in conventional UT, if the wedge delay was performed correctly, 0 here, which represents the probe to component interface, is also 0 here out on our A-scan. If the wedge delay is correct, 0 appears here. If the velocity and wedge delay are correct, then we will also see the correct sound path for a radius or depth for a side drilled hole. This ultimately is what the wedge delay calibration needs to do. So it was initially calculated at 54.97, and going through our wedge delay wizard will make a minor correction to that. Inputting the wedge probe and component parameters correctly into the group wizard is the most accurate way of arriving at the correct wedge delay. Use of the wizard on a new or unworn wedge normally is done to correct a slight angle error by adjusting the depth of the calibration notch. Mechanical handling errors, errors due to side drilled holes being measured at different angles often reduce the accuracy of the wedge delay. And as we can see, the size of this side drilled hole will have an effect on the accuracy of the depth reading. And for that reason, the radius is always a preferred method for doing this. when we use a radius instead of a side drilled hole, we are removing angle error from the equation. So we get a much more accurate wedge delay by not making it dependent on the size of the hole, the position the angle is hitting the hole, or any angle error as a result of velocity differences. The wedge delay wizard will change the UT mode for the range and display based on the type of calibration reflector that was selected in the wizard. So in this radius inspection, we'll see a sound path, and in the true depth, we will see a true depth. This will affect both how we set the range and how we position the gates to perform the wedge delay. And again, it's very important to note, make sure that you know that you're either in peak mode or edge mode, because how you calibrate is how you need to perform the application, because the readings will be relevant to the mode you were in when you calibrated. We are normally in peak mode for amplitude-based weld inspections and in edge mode for corrosion mapping and thickness readings where amplitude is not significant. So under the wizard calibration wedge delay, we'll apply this to all the angles at the same time and select start. Okay, in this type of configuration, and there's several different calibration blocks with different radiuses available at different positions. In this radius, is going to be a 100 millimeter radius that you see here. We could also select the 50. The longer the sound path, the greater the accuracy of the reading. We would select next in the wizard, and it's asking us to set the position of gate A over the target. So in a sound path target, like you see in the radius, we're going to have a radius type gate selection as well. Ensure that no other signals are interfering in the gate. And as you can see here, at about focal law 55 or about focal law 60, the wedge delay was exactly 100 millimeters. At 45, it was long, and at 70, it was short. Okay, here we see it's reading a 102 at 45 degrees. So this wedge delay for all of the focal laws is essentially going to bring them all to 100 based on a peak amplitude. We select clear the envelope, and we will, using constant steady pressure and couplant, move the probe over the radius, slowly exposing the exit point to the 50 and 100 millimeter targets. And when that is complete, we'll select Calibrate. You can clear the envelope and redraw the envelope as many times as necessary. Selecting Accept makes a slight correction to the wedge delay for every focal law based on the readings from the wizard. And as you can see here, under the sound path reading, SA, we'll see that it's at exactly 100 millimeters. A very tight, accurate wedge delay is really important for ultrasound inspection. And the trace that you see here allows a tolerance of about 1 millimeter, and that's only a visual indicator. So upon selection of Accept, we will also see a green W that is telling us that the wedge delay was corrected or amended using the wizard. Many of our applications that don't have a green W, it's not necessarily an indication that the system wasn't calibrated or wasn't complied with the procedure. Some of the companies have made a green W mandatory, and that's okay too for reasons of consistency, or that they just want that done every time. But it's just important to understand why and what that function actually does. So prior to moving on to sensitivity, we'll talk a little bit again about the wedge delay and velocity calibration and how it affects our data. Here we have a wedge delay and velocity calibrator on a standard IIW, and what you're about to see is I took a clock scan of the probe and slowly moved it across the IIW block, exposing every exit point to this position on the block. Okay, what that gets us in the software, and again, here we see a typical A scan. Here is the reflector from the 50 millimeter target, and this is the reflector from the 100 millimeter target in sound path. Menu display, A, S, and C scan. So I took a clock inspection after wedge delay and velocity calibration to verify the accuracy of the inspection. So on any A scan, we'll start at 50 degrees. We need to achieve 50 millimeters and 100 millimeters on the cal block. That's only possible if a wedge delay and velocity are accurately entered into the software, either through the wizard or through the process of the calculator initially in the group setup wizards. Moving to a different angle. $50, $100. $50, $100. So we can prove that for 45 to 70 degrees. This is very much the same function that we've always done with conventional UT. We're just have tools in the software that allow us to do it over many A scans simultaneously through a wizard that makes it faster than calibrating it by simply manually dialing in the velocity and wedge delay and going back and forth. For each beam, we can see that at 59 degrees, we had a wedge delay of 31 microseconds. And if I were to change the angle, we can see that the beam delay is different for every angle in the sector scan because it has a different time of flight through the wedge. Moving on to sensitivity. And again, I'm taking about 5 presentations and maybe more than 100 slides and combining them into a condensed 1-hour version. In the download that you receive from this webinar, you'll receive the full version for all of these that has a lot more information and more examples in the software. So before we move to sensitivity and TCG calibration, we wanted to refresh everybody about what actually amplitude means to these displays. And what amplitude means is color. We're converting amplitude here to color here. I can tell by the color of something in the C scan, B scan, or D scan what its amplitude is. And these color palettes are designed specifically for ASME type amplitude drop sizing, meaning that I can see a very clear break at 6 dB here and at 3 dB here. The ruler to the right displays the default color palette that can be modified by the user, and it's a 2D representation of the A-scan data. It's impossible to manage 50 or 100 A-scan displays, so it has to be converted to color so that we can see multiple A-scans at the same time. The MX2 sensitivity calibration wizard is designed to equalize the amplitude of all of the A-scans at one time using the wizard. The function is also called ACG, or angle corrected gain, by the ASME codes. In conventional UT, sensitivity calibration is achieved by manually adjusting the gain until the reflected signal is at 80%. The function of the sensitivity wizard is to do this for all A-scans at one time, making it fast and practical. Our codes and procedures are very clear about inspection sensitivity. It's directly related to the reject rate that was designed by the code. Little holes produce a very sensitive inspection with lots of rejects, typically, where big holes are a less sensitive inspection that would allow more flaws. Depending on the code, the sensitivity of the inspection could be very different. An AWS fabrication weld could have flaws that are not permitted in a closure weld for a pressure vessel or piping. The ASME has very specific calibration requirements that require all beams to be used in the examination shall be calibrated in accordance with the ASME Section 5, Article 4. The short version of that is that any A-scan we're using in our scan plan coverage requires a calibration similarly to a conventional UT. So prior to sensitivity calibration, the lower angles will detect the target at a higher amplitude than the higher angles due to a longer sound path in the material and through the wedge, causing more attenuation. In other words, when I exit the setup wizard, prior to performing the calibration, at 45 or 50 degrees, I have a high amplitude signal, but as I move the probe to look at the same reflector on the high angles, I'll see a much lower amplitude. So one of the first things we have to do is correct that prior to building the TCG. In the examples below, the MX2 general gain of 24.1 was entered for all focal laws in the group. After completion of the sensitivity calibration wizard, each focal law applies a calibrated gain offset that is added to the general gain. So both of these angles, 50 and 65, have 24.1 dB of what we call hardware or general gain, and then an offset gain from the UT beam menu is added to every focal law to bring them all to 80% amplitude. The target used for the sensitivity should be in the general area of interest for the inspection or specified in the procedure. General rule of thumb is to select a target approximately 1.5 times the thickness in true depth. So a side drilled hole selection for sensitivity that is too shallow or too deep results in poor results and can impede the construction of the TCG if that's required. And by true depth, I mean this is a 12 millimeter thick weld. So we go down 12 millimeters in true depth, back up 6 millimeters, and then we select the closest calibration block side drilled hole that we have to that to do our initial sensitivity inspection. This will ensure that the slope created for the difference in each A-scan is appropriate for the area of interest of the inspection. If I create that slope on a TCG point or a side drill hole here, it would be seriously distorted when we have enough range to get to the weld. After completing the group wizard process, position the probe so that the calibration target can be seen in the S-scan and ensure that it is at the correct position and amplitude. Enter the wizard to calibrate the S-scan for sensitivity AGD by selecting Wizard, Calibration, Ultrasound, Sensitivity, All Angles. And again, our calibration point for this example, we're going to use the 15 millimeter deep side drilled hole from an IIW block. So we enter the reference, which in most our application is 80%. That means that whatever the signal is in the gate A, the software is going to add dB to make that 80%. We have a tolerance window of 5% that can just be a visual indicator. The sensitivity calibration has a feature in it that allows this to be done in stages. If the calibration hole or notch you're using is too close to the edge or is incapable of gating all the way across the S-scan without interference from the side, the software allows a two-step process where part of this can be done initially and then a second part done the same way, preventing a large echo from interfering with our ability to create this envelope. Set the start and width of the gate in this step of the wizard directly over the calibration side drilled hole. So a 15 millimeter hole with a start position of 10, a width of 10, and a threshold of 10 for the gate allows that signal to be seen in the gate, creating the envelope in the calibration window. Select Next, and we have a step for gain compensation. This is a feature that's fairly unique to Olympus we created to allow a wider sector scan to be calibrated or a longer time of flight. So one of the limitations of this display is that no matter what my setup is, my first focal law must be below 100%, and my last focal law must be above approximately 10%. So whether I made the sector scan 45 to 70 or 30 to 80, whatever I'm doing, I've got to maintain that ratio or I'm not able to complete the calibration wizard. If I use a large side drilled hole, it's going to affect my ability to do that. If I use a side drilled hole at a very long time of flight, the difference between the 45 and 70 is very great. And again, from 100%, slightly below 100%, to approximately 10% gives us about a 20 dB range of where the first focal law and last focal law cannot exceed. So what this gain compensation does prior to calibration, it adds gain based on the sound path. In other words, the high angles would receive more gain prior to calibration than the low angles. And when the calibration window is created, it takes that into account. So whether you understand what I just said or not, as a regular user of phased array, the working man's result of that is that I can complete this wizard with a wider sector scan or on a hole deeper than I would be able to without use of gain compensation. So as I move the probe across the component slowly, the software is remembering the peak amplitude of every focal law and recording it with an envelope trace. Any signal that's above 100% or below approximately 5 to 10% will have an enormous error and won't allow the wizard to create the calibration. If I'm not able to complete this calibration window here, I must reduce the S-scan angular range or adjust my calibration target. Sometimes focusing can have some effect on this. The majority of our applications are typically unfocused because they're designed to be done with a code like the ASME or the API or AWS using a TCG. It must be contained completely within this form to be able to perform the calibration function by selecting the button here. Successful sensitivity calibration of the S-scan is visualized by repeating the probe movement over the calibration block with all focal laws corrected to 80% amplitude. Any focal law over 100% is saturated and cannot be corrected. So we can select the Calibrate button repeatedly until all of the A scans are within this tolerance within the window. The only reason that this window changes upon selection of calibration, where the line would not be within the tolerance, is because of couplant and pressure. It's directly related to amplitude, and you must maintain the same couplant and pressure. It's a very simple math equation the software is performing here, and it must use the same couplant and pressure to be able to complete the repeatability within the tolerance window. So prior to moving to the second option, again, we'll take a quick look at this on the instrument itself. On the instrument, after sensitivity calibration, we will see an S that's telling us that the wizard has modified the sensitivity, and inside every focal law under UT beam, we now have a gain offset associated with each focal law. On the 51 degree that we see here, our gain is 25.8 plus 3.8 to bring the signal to 80%. So after calibration, there's a good feature we use under data source to display the highest amplitude A scan inside the window. This allows me to move the probe and have the A scan follow. So I can go to any focal law. Make sure you have plenty of couplant. On any focal law, we should have very close to 80% at 15 millimeters in depth. 80% under amplitude, 15 millimeters under DA. $80, 15, 80, 15. That tells us that our calibration was successful for a 1 point, and sensitivity is essentially a 1 point TCG, and we can repeat that on the cal block with within about a half a dB repeatability. So there's another option in addition to all angles for the sensitivity inspection. And there's a 2 or 3 angle option. In the 2 or 3 angle option, we select 3 or 2 angles, depending on which you selected. The software will base its calibration strictly on those angles and will automatically fill in the entire S-scan in between with a linear slope. Somebody asked the question, for the side drilled hole, do you enter the center of the side drill hole or the depth of the side drill hole? Normally, we enter the center, but we need to know on a side drilled hole that's related to the time of flight calibration, not the sensitivity. The sensitivity need not know anything about the depth or time of flight. It's strictly amplitude. But in the wedge delay, every angle is going to hit the side drilled hole a little differently, and it is relative to the position. It's another reason we use radius instead of side drilled hole as the preferred method. So on our 3 option here, why would we do that? We call an empirical calibration a calibration based on real readings. They take into account frequency, everything. And a theoretical calibration is one that is arrived at with math based on some premise, which may be a reading. So this calibration is a combination of them both. We're going to take an empirical reading on 3 angles, and the software is going to create a linear slope to fill in the rest of the S-scan. One of the reasons we do this is because sometimes it's not possible to create a 75-degree sector scan because at the high angles, depending on the probe pitch and aperture, the beam mode converts and is no longer valid in the time of flight or calibratable because it's traveling under a different velocity. So when we can't complete the wizard for the 75-degree shear wave, but we want to include it because it's very useful for identifying and finding defects, we would enter a 75-degree sector scan, but only select the 70 as one of our 3 angles. This way, the software will fill in the rest of the predicted amplitude and not turn it solid red, which would impede our inspection. When using the 3 or 2 focal law option, we'll see a different type of S is available here, as indicated that the calibration sensitivity wizard was completing with a combination of empirical and theoretical and not a pure empirical like we saw in the last slide. So as part of the sensitivity calibration, we're going to include the TCG. What is the effect on a one-line scan inspection without a TCG calibration? The effect is it is impossible to set the inspection sensitivity where flaws are detected at a similar amplitude throughout the weld volume. Flaws are missed or are detected over-sensitive. Okay, the C-scan on the left has a complete calibrated TCG. And it is a TCG made from this block, a standard nab ship block with side drilled holes. Any angle from any position detecting any of the 4 side drilled holes can be displayed at 80% amplitude and at the correct depth. Ultimately, that's all a calibration is. Without the TCG, as we see here, the shallow side drilled hole, and this is 45 millimeter, this is 45 degrees, 70 degrees. And then this is the 12 millimeter and the successive deep holes. And as we can see, as the hole gets deeper, or as the angle gets higher, it's a very small indication because it hasn't been corrected. So it's very difficult to do a long sound path good inspection without the use of the TCG. And that's specifically why they are required by most of the codes for new weld inspection that we work to. When we look at this in the software, this represents the calibration that we just saw. One probe looking at a series of side drilled holes. Whether you're using math, empirical readings, or some combination of the both, ultimately, every one of these needs to be 80% amplitude and detected at the correct depth for every angle in our inspection. If that's possible, when that's possible, you can claim code coverage similarly to a conventional UT inspection for every angle in the material. So at 49 degrees, as I move the probe over the side drilled hole, we see 80%, 80%, 80%, and 80%. So each of these A scans has 37 dB applied to it. Every A scan was calibrated for sensitivity and has a gain offset associated with it under the UT beam. Additionally, every TCG point for every A scan also has an associated gain offset. Through the wizard process, the software builds this. So at any given angle of any position, I have what the code or procedure intended as a representative reject rate of an 80% signal. Our next webinar next month for the advanced deals strictly with TCG for the whole hour. Manual, empirical, and theoretical in how and why we use those. So I recommend if you're struggling with the TCGs, please attend the next month's because it'll have a lot more information regarding this. So what is the difference between a TCG and a DAC? We hear both of those terms used synonymously, interchanged with each other, and in fact, to the reject rate or to the intent of the code, they are exactly the same and will produce the same result. Where a code is specifying a DAC, distance amplitude correction, like you see here, that can either be converted to a TCG or can be built as a TCG. These two displays are showing the exact same beam reproduced on two groups, looking at the same flaw from the same position. The reason DACs are somewhat outdated is that we cannot convert them to color for the color palette. A reject in this part of the range would have a different amplitude than a reject in this part of the range, like you see here. Whereas in a time-corrected gain, the color is consistent across 80%, 40%, or 20% for the entire digitized range. This TCG function allows color-coded displays both in phased array and in conventional UT. The DAC does not permit that, so I must look at an A scan to visualize the DAC on every single flaw, which in some cases is not desirable. It's more difficult. Both of these provide the exact same information and code compliance. So in the TCG, just like the sensitivity calibration, we're going to use a series of side-drilled holes and complete a similar wizard in succession. The only difference between the TCG is that I cannot have a negative gain. So my focusing and my ability to separate one flaw from another becomes an issue. But as the wizard is completed and next point is selected, we're going to build a series of TCG points to include the gain offsets that make every one of these 80% amplitude. And in the end, we will have a table built. So for the 60-degree focal law on the fourth TCG point pictured below, what is the total gain applied to make this 80%? Through our wizard steps, we first set the general gain and completed our sensitivity calibration, which is basically just a one-point TCG. In the wizard process, we built TCG point 1, 2, 3, 4. So the fourth point, as in the question, at 25 millimeters, had an 8.1 TCG gain, 0.1 offset gain, for a total of 49.9 gain at 60 degrees. Every one of the focal laws would have a different table. The only reason we use the wizard is it allows us to do all of that at one time. But it's essentially exactly the same function as a single channel conventional UT flaw detector wizard. So that was a very quick overrun of a quick run through of the velocity, wedge delay, sensitivity, and calibration. This video and all of the supporting documentation, including the full PowerPoint versions of these lessons from the MX2 training program, and the 3 data files that you saw in OmniPC are all available in one link that people will receive when they get the follow-up from this webinar. So we've run out of time. I'd like to thank everybody in attendance. Again, this was one of our biggest turnouts. Please come back next time. And I will turn this over to our moderator to say goodbye. Thanks again, everybody.
Thanks, Chris. On behalf of Olympus NDT, I'd like to thank Chris Magruder for his participation in today's event. Thanks to all the attendees for joining us. We hope this material was informative and useful to you. This webinar, along with the Q&A, will be archived on our website at www.olympus-ims.com. Everyone who registered for this event will receive a follow-up email with links to the archived presentation, as well as links to download the data files used in the presentation, as Chris alluded to. Part 4 of this series will be on Wednesday, April 24th at 11 o'clock in the morning, U.S. time. Be sure to sign up on that on our website for that event. That's going to do it for today. And again, thanks to everyone for participating, and we'll see you in April.